Welcome back to our videos about convergence testing for infinite series. In this video, we're going to talk about the direct comparison test. And before we do, I just want to revisit a very similar feeling theorem that we've had in the past. And it's called the sandwich theorem. And so this theorem is used to test sequences. And so for example, if you're given a rule for the terms of a sequence and we want to know, does the sequence converge? So in other words, do the terms turn into something? Or if we are looking for the limit of any expression, really, it doesn't have to be in the application of sequences, but if we're looking to find the limit of something, the sandwich theorem says that if we can essentially sandwich our function or our sequence between two sequences whose behavior we know, and if we can show that the two on the outside kind of go to the same limit, then naturally whatever's in between those two should also have the same limit, because when we're dealing with infinity, essentially over the long run, towards the end, as we get closer and closer to infinity, as if the series on the ends are approaching the same thing, then the series in the middle should also be approaching the same thing. So graphically, kind of a way to look at it is like this. So if my series is given here, let's name my series in red, we'll call it f of x. If we can find a series that we know will always be, for better or for worse, below f of x, so that green function, and then if we can find another function who we always know will always be above my function, we'll call it that blue function. If the limit of my blue function, we'll call this one h of x, as x approaches infinity is some value L, and also the limit as x approaches infinity, and we'll call this one g of x is also L, well then the conclusion we make is that the limit of f of x will also be L. But the tricky part is we have to show that h of x over, whatever interval to infinity, so from wherever we start, and it doesn't matter where we start, but call it our starting value, we'll say from a all the way to infinity, we have to kind of prove that from a to infinity, h of x is always greater than f of x, and also g of x is always less than f of x. And so the tricky part is finding the two functions, or in this case, in this application, finding the two sequences whose behavior will always kind of fit that description. So the function that we're going to look at first, or the easiest function to look at, is this function here involving the cosine of n. So here we have the terms of a sequence, and again, it applies to a function as well as a sequence, but the idea here is that we know something about sines and cosines in that they're always going to be maxed out at 1, and the minimum value will be -1. So anytime we have a trig function, we know that there's a top and a bottom for that trig function, or depending on what the amplitude is, it might be a little bit different than 1 and -1, but the idea being that you always have an upper and a lower bound. And so because we know that cosine of n will always be less than 1 or between 1 and -1, it then tracks that if I take that cosine and divide it by n, as long as I do the same thing to both sides of that expression, it's going to remain true. So we now have set up our criteria here, and so if we look at our squeeze theorem here, it's also called the sandwich theorem, we can now show that, okay, the limit of this left-sided function as n goes to infinity is 0, and we also then know that the limit of the right-sided function as n goes to infinity is also 0. Therefore, we also know now that the limit of this sequence as n goes to infinity, cosine of n over n, must also be 0. So we have to set up our inequality, and we are basically sandwiching our function kind of between those two outside functions. And that's how that sandwich or that squeeze theorem kind of works when we have functions. And the tricky part is making sure that we have two functions that create a true inequality. And so now as we kind of look at this direct comparison test, it behaves very similarly to the squeeze theorem in that we have to create an inequality where we have functions that are being kind of squeezed together. Maybe even a better example of something we should know is the comparison test for integrals. And so if we have an improper integral, the comparison test kind of does the same thing. It sandwiches our function between 0 and another function to say that yes, the integral converges, or if we set it up in a different way, it'll say that no, the integral will diverge. So the direct comparison test is also very, very similar to that comparison test for improper integrals. So how does it work? Well, the conditions that we need to use this for is that a of an, our rule, has to create positive terms. So in other words, we have a non-alternating series. So anytime we're doing these comparison tests, all of them except for one require positive terms. So the condition that you're going to give right off the bat for any of these convergence tests is we've got positive terms, provided that that's true. So in other words, it's a non-alternating. That's probably the biggest thing that we're looking at. There are some other situations where you could have negative terms depending on what n starts at, but in general, it's just, the biggest thing to look out for is it's a non-alternating series. The best time to use this, when the simplified end behavior model for the series is a p-series or a geometric series whose convergence or divergence you know. There are other situations where we could use it, but these are the best case scenarios to use this particular test. Now, there are times when this test is not going to work, and we have another comparison test in the next video that will kind of talk you through, well, what do we do when I can't use this direct comparison test? Now, this test is very, very picky, so here's how this test works. We are going to state that the terms are positive, and then we have to create a correct inequality, and this is really important. So essentially what we're going to do is we are going to pick a known series. So we pick a known series that we know about. So for example, we would let b of n equal like the harmonic series. We know that this diverges. Or we'd let it be, a p series that we know converges. But we want to pick a series that we know about. And essentially, as you do this, you'll kind of get a feeling for when you look at a series, what it's going to be, kind of its divergence or convergence. And in general, if you have like something that is almost the harmonic series, it's probably going to diverge. So like when I say almost the harmonic series, I mean like 1 over 2n or 1 over 2n plus 1 or something like that. That's going to be almost the harmonic series. It's going to be really similar to that, and you're going to want to pick to compare to the harmonic series. Another situation is if you have like n squared, or if the end behavior model if the end behavior model simplifies to the harmonic series or to a p series or to a geometric series or to something that you know what's going on with it, that's when you want to do this direct comparison. Now, it is very tricky, so let's pay attention to our inequalities here. If you are picking a value or a series that converges, so you think that it looks like a p series where p is greater than 1, or you think that it looks like a geometric series where r is less than 1, then you need to make sure that this inequality right here is true, right here. In other words, your series that you are choosing has to be always bigger than the series given in the problem. Now, if you think that your series diverges and you're comparing it to a divergent geometric series or the harmonic series or something like that, in that case, you are going to want to make sure that your series is smaller than the given series. Okay, so notice that the difference between where b, your series that you are picking, that's that simple one that you know about, is. So if it converges, yours has to be on the outside, because the idea here is that if we have a convergent series, the only way that our series can converge is if it's between 0 and my series, so that my series and 0 squish down, and kind of like that sandwich theorem we talked about in the beginning, it converges it down to something, whatever it happens to be. Now, if you pick a divergent series, the idea is that your series has to be below the one in our problem, because if the one I pick, say I pick the harmonic series, diverges, my mental image is that here's 0, here's my series, it's going to push up and out and kind of make the other one explode and diverge to infinity. And that's kind of the visual that I have. And so you have to make sure that you have these inequalities correctly stated. Okay, and this is very much like the comparison test. Comparison tests work the same way. We used functions. Either we had a function that was bigger and it squeezed and sandwiched it in between 0 and itself, and it said that, hey, the one in our problem is converging, or we had a function that was below the function in the problem that was pushing up and out and kind of creating this divergent scenario, proving that our function in our problem was also divergent. So, and then the last thing we do is we state our conclusion. So let's see how it works, and kind of state our situation, or state our conditions, and then run our test to make sure we know how it's going to work. Okay, so the first thing that I'm going to do when I look at the series is I'm going to look and see, first of all, I've got positive terms. They seem to be decreasing. The nth term test, if I were going to do this limit, the limit would be 0, so it's not like I have a divergent series. So what I'm going to do is I'm going to look at the end behavior. And the end behavior model is a convergent p-series. So 1 over n squared, that series would converge. So when I see that I have a convergent p-series in my end behavior model, so remember that's the largest exponent on the top, largest exponent on the bottom, it's the dominant part of the function in the top and the bottom, it's the ratio of those two dominant functions. So as I look at this, I see that I have a p-series that's going to converge. So I'm going to state my conditions. I'm going to say that my terms are positive. Then what I'm going to do is I'm going to compare to 1 over n squared, which converges, and I'll say that it is a convergent p-series where p equals 2, which is greater than 1. So I'm saying that I'm comparing it to this convergent p-series. So now I'm going to set up my inequality. I'm going to say 0 is less than or equal to. Now, because I have a convergent series, so here's where it gets really kind of dicey. I need to make sure that my series, 1 over n squared, is on the outside. Anytime I pick a convergent series, it goes on the outside. If I pick a divergent series, it goes in the middle. So 1 over n squared has to be on the outside. So here's where it gets tricky, because I have to make sure that this is in fact a true statement. Now, let's talk about when we add things in a denominator. Let's suppose that so n equals 1. So this has to be true for all values of n. So I'm going to pick a value. I'm not going to pick 1, because sometimes 1 is a little bit, crazy. You can start with 1, and as a matter of fact, if you had 1 for n, this would be 1 over 2, and this would be 1 over 1. That's a true statement, but it has to be true for more than just n equals 1. So we have to check it for a couple other things. So if I let n be 2, for example, this would be 1 over 5 and 1 over 4, and 1/5 is less than 1/4. So here's kind of the general rule of thumb that you're going to be looking at. If your denominator is adding a value, then that denominator will force your overall fraction to be smaller. So when we are adding 1, or even if it was adding 5, adding 4, if we're plus something for your end behavior, if that's the only difference, then that quantity will be smaller than the quantity without the plus 1. And if you ever forget that, just plug in a few values of n and make sure that it's true. Generally, if you can test, 2, maybe 3 values, it's probably going to be okay. But whenever we're adding something in the bottom, when the bottom gets bigger, the fraction gets smaller. So I've stated my inequality here, and now I've said that I'm comparing it to a convergent p-series. And so because I have this situation and because my inequality is true, I can now make my conclusion. Therefore, my series 1 over n squared plus 1 also converges. So, and we can Sometimes we leave out the n equals 1 and the infinity because we're talking about the series as a whole. Doesn't matter where n starts. The series either converges or diverges. Whether we start at 1 or start at 100, it's going to be the same result no matter what when we're dealing with infinite series. So here's how my direct comparison test works. So let's take a look at another example and kind of see how it plays out. So here I have a series, and just looking at this, I have a feeling that this is going to diverge. And so what I'm going to look at is the n behavior model is very similar to a geometric series where r is going to be 5/3. And so I see those powers of n and it resembles a geometric series, and I have a feeling that this is going to diverge. I can also make an argument that if I tried the nth term test, the nth term test would probably also reveal that this limit is probably not going to be, it's probably not going to be 0, although it might be a little tricky to find. So I'm going to keep going with my direct comparison test, and I'm going to compare it to a geometric series. So here's what it's going to look like. First of all, when n is 1, from 1 to infinity, my terms are positives. So then I'm going to compare to this series. The n behavior model is going to be 5 to the n over 3 to the n, which is simply the geometric series 5/3 to the n, which diverges because r equals 5/3, and that's greater than 1. So I'm going to identify it as geometric. So any information I can give to help support my case, I want to make sure that I include that there. So the geometric series, we have a divergent series. So now, remember, if I'm comparing to a divergent series, that series that I'm comparing to has to be in the middle of the inequality because it's going to push it outward. So I'm going to make my inequality, and then I'm going to make sure that it's true. So let's take a look at it and make sure that it's true. Now remember, in the other example, we were adding something in the denominator. Here, we are subtracting something. And when we subtract from the denominator, it actually makes the whole fraction bigger. So anytime you have a minus, then that is going to be a bigger value than its n behavior model when we have -1 in the bottom of our fraction. So in this case, this inequality is true. So far so good because I need it to be true. If ever it's not true, then this test is not what you want to do. So let's make our conclusion. So because we have this true inequality, we're comparing this geometric series that diverges. My terms are positive. Therefore, here's my conclusion. The series in my problem, 5 to the n over 3 to the n minus 1 diverges. So, as easy as that. The key is you have to make sure that you have this true inequality. Okay? So let's see another one here. Let's take a look at almost the same problem, but this time my inequality is not going to be true. So this is going to pose a problem because if I'm going to compare to, do a direct comparison to this problem, I'm going to compare it to that divergent geometric sequence. And here, if I try to build my series, here's the problem. This is not a true statement. This will not be smaller than this because we are adding 1 in the bottom. So this is a false statement. So the direct comparison test will not work. Well, there might be a way, I don't know. But at this point, I would abandon the direct comparison test and I would go on and I would choose a different test. And so the test that I would choose is something called the limit comparison test. And so that's what we're going to be talking about in the next video in the series. So check out how we're going to solve and show that this diverges using that limit comparison test, and that'll be in the next video. But for now, you can try that direct comparison test and make sure that you are paying close attention to those inequalities so that you can make sure that you are picking a true inequality that supports your claim and allows you to make a correct conclusion. So practice, you've got this.